Hey guys, my name is Matt. I'm a 9th grade student at Sir Winston Churchill Secondary School in Vancouver, Canada, and I've decided to explore the STEM route for the Crown Education Challenge. For this project, I've created a simulation program of the iconic SIR model, beefed up with dimensions such as population size, social distancing, transmission risk, and many more, to demonstrate how seemingly simple fundamental factors contribute to the spread of diseases. Why don't we take a closer look? There are many interventions that we as individuals or as a society can take to prevent the spread of diseases. However, some people don't see the value of these actions as they are biased to believe that they cannot change the outcome of a disease. This project seeks to change some of those biases by educating users through the entirety of the SIR model, which is the most common compartmental model in epidemiology, used to track populations that are susceptible, infected, and have recovered over time. The engagement factor here is the user-friendly simulation program that contains a wide range of dimensions that users can change. Hopefully, the education component of this project happens when users begin to experiment with different dimensional configuration, each time creating a new outcome visualization based on these decisions. The research component was, by far, the largest part of this project. We start with the base SIR model equations, a system of differential equations. When a new variable parameter is introduced, I cross-reference with existing literature to find the agreed upon figures as well as how to relate to the base model, biasing towards papers that are more cited. For example, when contact rate was introduced, I saw that a couple of sources found an average to be 6 per day, which became an input factor to calculating the transmission rate beta. I then coded it in as such. For more detailed write-up on the SIR model and my parameters, check out my website. The biggest obstacles encountered was finding an adequate number for each intervention. I overcame this by cross-referencing with many scientific papers specific for behavior and making best possible estimations. I created my simulator using the Java Swing library with JPanels on JFrames. You can think of the JFrame as an easel and the JPanel as the canvas. The buttons and sliders could be considered the paint. After some time tweaking, everything fits perfectly. Deploying this onto a website would make the program much more accessible. However, the updated nature of the JSwing library isn't conducive to doing so, and I vow for the next version to be built on JavaScript. Why don't I show you my simulator? The graph is split up into 3 area charts, representing susceptibles, infected, and recovered. At each time point, if you add up all 3 of the charts, it should equal the population size. Each factor and parameters affect the SIR model. Since the area is defined, the population size changes. The density affects the contact rate. The disease duration changes how long the disease stays in person. This will vary between people because of their immune system, so I just took the average. If you are infected and encounter another person who is susceptible, you have a chance to spread the disease. This is the probability, and it's also called the transmission risk. The next part is the juicy part. This is where the interventions are. Each intervention can decrease the probability of transmission, or the transmission risk. Researching scientific papers allow me to find the effectiveness. Adjusting the intervention sliders, users can see how their behaviors can affect the spread of diseases. Finally, there are presets. Presets show how known diseases such as COVID-19, SARS, or H1N1 spread. This simulator is far from the final version. For some next steps, I intend on modeling population tolerance and economic costs as well, once more research on these topics surface. This would tie neatly into my plan to create a multiplayer game engine based on this simulator. Allowing players to control sections of the population, choose levels of interventions while juggling the cost of functions can really help them empathize with the decisions that public officials need to make every day. As more public data sets continue to publish, we can fine-tune our assumptions, adjust our models to best fit reality, and even further slice by dimensions such as country and population density. I hope you enjoyed this video. Please find the links to my GitHub, website, and downloadable simulator in the description down below. Thank you very much, and stay safe.